Hi everybody, sorry I have to be gone again. Um, Hoping to be back by Thursday, but we just gotta see how things play out. Looking forward to seeing y'all. Okay, so here is what we're gonna take a little look at today. We're gonna talk about the very basics of rocket propulsion and why rockets are able to move. Also going to talk about why padding decreases damage if there's any kind of a collision or an impact. That definitely is related to impulse and momentum. And then we're going to look at the delta V, change in velocity of a system when mass changes. Up to this point, we have talked about mass being constant. This isn't a complicated example, but it's an example of how you can have a circumstance where the mass changes. Practice problems 5.3 have been posted. Got 4 problems, and then there's an extra special challenge problem that's put in there too, if you like extra special challenges. Little reminder just to make sure that you are getting Lab 5.1 done. There are 2 days, 2 parts. Tomorrow you will have an open note quiz, and Friday we will wrap up linear momentum. So let's just talk about the basics of rocket propulsion. So a few things to ponder here. Okay, well, we're going to start with boats. Boat with a propeller. Think about what does that propeller push against to make the boat go forward. Don't look for any trick curveball questions on this. What does that propeller of a boat push against? 3, 2, 1. Yeah, it pushes against the water. Another example. Let's take a prop airplane. So airplane with propeller, not a jet. So what do the propellers of an airplane, or maybe a helicopter, push against? Again, don't look for any curveballs on this. So the boat's propellers push against water. The helicopter propeller, a propeller on an airplane, pushes against air. Jets work a little bit differently, and we don't need that as an example. Here's the question. What do rockets push against? So please pause this little lecture for a minute and just discuss with each other what rockets push against. All right, hitting pause. And we're back. Okay, so some people might have said against the air, some people might have said against the ground, but rockets work in space. Got a few questions here. So if you look at this picture, this is a space shuttle, which is no longer in operation, but it is a good example. The orbiter, the part that looks sort of like a plane, that's where equipment and the peoples are. The big maroon-shaped thing underneath it, that is a fuel tank. It's full of liquid hydrogen and liquid oxygen that feeds those 3 engines, those 3 rocket engines on the orbiter. And then the 2 white rockets that are strapped on the side are called solid rocket boosters. That is because the fuel in them is not a liquid, but it's a solid. Think a really big, really sophisticated bottle rocket. Same basic idea. Bottle rockets are solid fuel rockets. Another question. Okay, so all that fuel packed into those solid rocket boosters, all of the liquid oxygen, liquid hydrogen that's in that big red tank, is it made of matter? Not a trick question. I hope you're nodding your head up and down, maybe even saying yes. Matter has mass. This might seem obvious, but just hang on to that thought. Matter has mass. Liquid oxygen has mass, liquid hydrogen has mass. Turns out the main propellant in those solid rocket boosters is powdered aluminum. And then there's just a whole boatload of oxidizer with it. But all of that has mass. Think back to your chemistry now. When you have a chemical reaction, does the mass of the products end up being smaller, bigger, or the same as the reactants? In other words, when you have a chemical reaction, do you gain mass, keep the same amount of mass, or lose mass? You cannot create or destroy matter. So all of the products of a chemical reaction have the same mass as all the reactants. Well, the reactants is all the fuel. Think about when you burn that fuel, all of that mass is going backwards. Turns into a figure skater problem. One amount of mass goes one way, so the other amount of mass goes the other way. The only reason why we burn fuel is because it makes all the little particles in it move very, very fast. So you can have a small amount of mass carry a lot of momentum. You could have a fuel that focuses more on having a lot of mass but not moving so fast. The problem is the mass has to get packed into those rockets, and so mass is difficult to move. So if you can have something where you can make it start moving really fast, in this case through burning. When you burn things, it makes all the little particles move super fast. But if you can have a little bit of mass move really fast one way, that will impart an impulse on the rocket and everything going the other way. So what you need to know about rocket propulsion, get ready for some very simple notes. What you should write down about rocket propulsion is that rockets throw mass. Think about if you were holding a medicine ball, big heavy medicine ball, and you're standing straight up. If you throw the ball forward, think about what direction you go. You go backwards. So it's the same basic idea. You could have some really big person, strong, throwing rocks out of the back of the space shuttle, and that would make it move a tiny bit. It would not be effective. So you do not need to write this down at all. But this is a simplified formula talking about rocket propulsion. And I'm just going to pick it apart, but you do not need to write this down. That delta V on the left, that's the change of a rocket's velocity. This equation totally ignores any gravity, so this would be way deep in outer space, no gravitational influences. So this is the delta V is how much faster the rocket goes in one direction. The VE is the velocity of the exhaust in the other direction. Well, if you look what's inside that natural log, there are a couple of M's. M means mass. So it turns out it's the ratio of initial mass of the rocket and everything, including the fuel, and the final mass. So what it's just looking at is when you start off with a certain amount of mass, that initial mass, that doesn't give you as much of a change in velocity because more mass is hard to move. But as that mass reduces until it gets to the final mass after you've burned all the fuel, you are getting much easier to move. So you've got just the rocket and not the fuel. So again, both those masses are the fuel and the rocket. So big things are hard to move, light things are easier to move. This is just in case some of you might be interested. All right. I would like you to follow along with me on a little imagination. Going to ask a couple of questions, and it may not seem obvious where we're going with them at first. But just bear with me. We'll get to the point. unlike most days in my class. So let's say you're holding a bag of potatoes. Now, someone's trying to take those potatoes away from you, and you're holding them very tightly, and they have to pull with 25 pounds of force in order to rip them out of your arms. Now, you're holding on to these really hard because you love potatoes. Someone's trying to take them away. So pounds is English imperial measurement unit for force. So we can convert force in pounds by 4.448 to convert to newtons. Turns out 225 pounds is approximately 1,000 newtons. It's really 1,000.8, but 1,000 newtons is going to be close enough for what we needed to do to have some easier math. So that's first question. It's about potatoes and your love of them. This is strange. Second question. This might not seem to be related to potatoes. So let's say you have a 10 kilogram object. So a 10 kilogram object is initially moving at 30 meters per second, and it comes to a stop. So think about how you determine impulse. Impulse is a change in momentum. So it's whatever the final momentum is minus whatever the initial momentum is. The mass here is not changing. We have a 10 kilogram mass, so we can write it this way, because momentum is mass times velocity. Our final velocity is 0, and our initial is 30. So when you take a 10 kilogram object and you change its velocity by 30 meters per second, you will have a 300 Newton second impulse. Okay, hang on to those thoughts. So here's the scene. You're in a car. You're traveling at 30 meters per second, and you run into a wall. All right, so you have bought the world's safest car. You got your seatbelt on. You are okay. We don't want any tragedies to worry you. But you have unfortunately run into a wall, and your car goes from 30 meters per second to a stop in 1.5 meters. So you got a big car, and the front end crushes enough so that it gives you 1.5 meters to slow down. Now, you could easily plug this into a kinematics equation and figure out that slowing down from 30 to 0 in 1.5 meters takes 33 thousandths of a second. Way in your wheelhouse. So let's say you were going old school. Child safety takes a back seat, so to speak. Yeah, people used to just drive around with their babies on their laps. That is not only unwise, it is now currently illegal. So people are thinking, oh, it's a baby, you know, it's this little creature. I love it so very much. So if something happens, I'll just hold on really tight. It's just, surely I can hold this thing. So we have established that if you take a 10 kilogram object and you change its velocity by 30 meters per second, that will involve a 300 Newton second impulse. And if the car here slows down from 30 to 0 in 1.5 meters, that will take 33 thousandths of a second. The question is, can you really hold on to the baby? Here's our equation for impulse. It's how much force is exerted for a certain amount of time. We rearrange it to solve for force. So we know the change in momentum, that's that 300 Newton seconds, and we know that you have to be able to counteract that impulse for 33 thousandths of a second. This is not looking so good. Time to use the child seat. Yeah, for those 33 thousandths of a second, that kid would feel as though they weighed a little over 1 ton. So no. So if you are curious, we've established that you can exert a 1,000 Newton force. That's that 225 pound force. The car would have to take 3/10 of a second, not 33 thousandths of a second. It would have to take 3/10 of a second to slow down, which means that you would have to come to a stop in 13.5 meters after traveling at 30 meters per second, which is 67 miles an hour. This is not a stopping distance that you get out of cars. Just for reference, stopping from 67 miles an hour in a very high performance sports car will probably take a little under 100 feet. And that would be a noticeable experience. If you did slow down from 30 meters per second to a stop in this distance, you would experience an acceleration of more than 10 times that of gravity. That is crazy. This would be harmful to you if you slowed down this quickly. So, yeah, you'd have to be pretty strong. Kind of like this guy. The Hulk cares about babies. Doesn't matter if they're a little homely. Hulk still loves babies. All right. Let's talk about why padding does something helpful for us. So we're going to go back to this idea of impulse. And a lot of people can't really describe what truly padding does. They understand that it's going to make a crash hurt less, but it's just kind of intuitive. They don't really know what's going on. You're going to know what's going on. What padding does, and you'll want to know this, any form of padding increases the time that it takes an object to slow down. Now, we just looked at a problem where, because of that car crash taking so little time, there's a huge amount of force involved in holding our baby. And anytime you can increase the amount of time that you are slowing down, you're going to decrease the amount of force it takes. So if we just do a little rearrangement of our algebra right there, to change the velocity of a mass in a certain amount, over a certain amount of time, gives us how much force is required to do this. And force is really what we're looking at when we say if a collision is going to be damaging or painful. So you could have a really significant change in momentum, but if you spread it out over a large enough time, you'd have no problem. You'd have no problem. Now, this isn't a really technical explanation of things, but it does say why padding works. So what I want you to know, what you should know, is that padding increases the time of an impact. And that is something that is very much in the fore when someone is designing helmets and padding for the sports or a car. It used to be that cars were just built to be sturdy and not to bend, not anything. That was what was thought to be good, make it strong. Modern cars are designed to crush in all the places where the people aren't. So during crash testing, you look at how much that front end of this vehicle is crushing, but the passenger compartment is staying pretty intact. You can see the airbags deploying. That also is a form of padding. That's kind of a more obvious form of padding. But the crush zones, the crumple zones of your car are padding. You look at this. That front end is completely destroyed. Look at the driver's side door. It's not even wrinkled. So all of the engineers that designed this car designed everything up to right at the beginning of the passenger compartment to crush, to absorb the impact. And then all the people inside are in this nice, very strong encasement, so to speak. Yeah. Feel like somebody should write a song to this. Any musicians in the group? All right, last thing. So this is how to talk about change in velocity when you have a change in mass. So we're looking at this case where we have this rolling cart. It's stationary. And we have a human who is running. They're going to jump onto the cart. Well, I think we all know what's going to happen. They're going to jump on the cart, and the human in the cart will start to roll forward. So we have this 60 kilogram human, 4 meters per second, jumps onto that 120 kilogram cart that had no velocity, no initial momentum. So he slides a little bit, but comes to rest, and he and the cart are essentially becoming one object. There is a coefficient of friction between the human's shoes and the cart, and so it takes a little while to slide, but still eventually comes to rest relative to the cart. And we're looking at essentially no friction between the cart and the ground. Question is, how fast are the man and cart going relative to the ground after the man jumps on to the cart? There it is. So I want you to pause this for a couple minutes and discuss how you would get this. Probably won't even take you a couple minutes, but please hit pause now. Pausing. And we are back. So let's see how we get this 1.33 meters per second. It's not bad. So we're looking for a final velocity. Well, let's talk about the momentum of the human before. This is not hard to figure out. We know the human's mass and we know the human's velocity. So there's 240 kilogram meters per second of momentum. Don't look for a trick on this. Momentum of the cart before the human jumps on it. Well, it may have mass, but it has no velocity. So therefore, no momentum. So the only momentum in this system is from the initial movement of the human, that 240 kilogram meters per second. After the human jumps on the cart and it starts rolling, that's still how much momentum is available to make everything move. Well, now we can solve for that final velocity. Because we know how much momentum there is in this system, the human cart system, and we know the total mass. It's not 60 kilograms, it's not 120 kilograms, it's 180 kilograms. So you might have wondered why I talked about the friction. Well, that was just to help you sort out whether or not you needed to use that. I have seen an AP question that does ask about the friction on top of the cart, a similar problem to this. So I just wanted to kind of have it out there to be aware that that's something that kind of comes up. The questions were usually pretty basic. All right, that is what I've got for you today. Thank you for your patience. I hope to see you soon. Bye-bye.